Hello everyone, my name's Ollie and I'm in charge of research here at Fathom and also part of the flood hydrology group at the University of Bristol. I'm going to talk to you about an enormous volume of work that Fathom has carried out with the support of the First Street Foundation and many other collaborators in developing a comprehensive flood hazard model of the US. It encompasses all major flood drivers and also projects changes as a result of a warming climate. Your first question might rightly be, what's the point of all this? Well, the answer is that geographers now have the tools at their disposal to fill critical gaps in flood risk understanding engineers have left in their wake. FEMA, a US government agency, has spent half a century and $10 billion building local scale engineering models across the country. But for all this time and resource, a recent report from the Association of State Floodplain Managers suggests that just 1/3 of US river reaches have ever been modeled. Of these, only 1/4 have been updated in the past 5 years, leaving an acceptable model for less than 10% of US rivers. Furthermore, these maps represent historical risk, and so in a shifting climate, they arguably become obsolete as soon as they're released. And all of this is going on as flood losses in the US spiral out of control. This has motivated the development of large-scale flood hazard models, which avoid the pitfalls of an inconsistent patchwork of local models. Being able to simulate a single return period flood for the whole US in a matter of weeks gives us the bandwidth to explore multiple flood frequencies and climate scenarios. Our work began in 2017 with the publication of our first version of the Fathom-US flood model in water resources research. This was a 30-meter inland flood model based on the ListFlood FP subgrid formulation, which permitted any river channel size to be modeled in one dimension by virtue of its decoupling from the model grid scale, while floodplain dynamics could be resolved in 2 dimensions. We used a whole array of data sources, principally from the US Geological Survey, including river gauge and elevation data. Since then, our group has done a ton of research to explore how the model can be improved and what it's useful for, from identifying areas that should be targeted for conservation to using our model to forecast the inundation from incoming hurricanes. This talk and its accompanying paper, which is currently under review with Water Resources Research, outlines the significant updates we have carried out on the US flood model. We couldn't do it alone. Fathom partnered with the First Street Foundation and dozens of other academic and commercial entities. Around 80 scientists worked on this model to produce the most comprehensive present and future flood model of the US ever built. The most important additions are shown here: a new coastal surge model, updating historical models to 2020's climate, as well as projecting future flood hazard, explicitly simulating the various flood responses to hurricanes, and improving all sorts of model components. First, focusing on inland flood modeling, we simulated the hydraulics again at 30-meter resolution, but projected the 30-meter water surfaces onto finer grids where they are available to capture the significant local spatial variation in flood depths. We employed a brand new river channel location dataset from the USGS, from which we built flow accumulation grids. A problem in version 1 was the use of hydrosheds, a product derived from global satellite terrain data, meaning channels were sometimes misaligned with their river valleys. Since channels are represented as 1D subgrid parameters, some flood flows would then not originate from the true 2D channel location. You can see illustrated in some of these images that the new data correctly aligns these channels. In the absence of any wide area measurements of the bathymetry of river channels, this has to be approximated in large-scale models. We do this by first assuming that natural channels can convey the 1 in 2 year flow at bankful discharge. In the old model, we thus calculated river depth using Manning's equation. A significant flaw in this approach is that Manning's equation doesn't capture backwater effects, meaning realistic water surface profiles were sometimes not generated, and bankful capacity was then often exceeded at more frequent return periods than we intended. In this version, we implement a new gradually varied flow solver developed by Jeff Neal to ensure that channels actually do convey the flows they're meant to. The paper describing this is currently under review. The way we estimate extreme flows is now specific to the United States. We use a regionalized flood frequency analysis to pool similar and proximal US Geological Survey river gauges and use these to predict flood flows in ungauged catchments. The old model, which is in orange in these plots, employed Andy Smith's global regionalized flood frequency analysis. You can see, particularly at short return periods, the new model has a much closer fit to extreme flows at specific USGS river gauges where we computed the extreme flows there in line with Bulletin 17C regulations. The First Street team also compiled a huge volume of flood protection information from multiple sources. Unfortunately for our field, which is so reliant on automation, there was no replacement for manual labor in this instance. We then used these data to augment the original 2-year bankfall flow assumptions and to ensure protected areas only inundated at frequencies lower than their design standard. In this example in Sacramento, you can see just how important the representation of flood defenses is. Our pluvial model, driven by extreme precipitation intensities and durations laid out in NOAA Atlas 14, means that flooding both in the tiny creeks and far from any river channel is also represented in the model. To generate the boundary conditions of our coastal flood model, we obtained the database of NOAA tide gauges. Since we're modeling hurricanes explicitly, we removed hurricane events from this record so as not to oversample. Gaps in the tide gauges were infilled using the tidal reanalysis data of the global tide and surge model, and we then updated these to 2020's mean sea level. For the hurricanes, we used Massachusetts Institute of Technology's hurricane event set, which is generated with 2020's atmospheric conditions derived from GCMs. The pressure and wind fields from the hurricane model were then input to a hydraulic model to generate coastal water levels. We then sampled from hurricane and non-hurricane datasets to generate the extreme surges. Since flooding in coastal areas depends both on what's going on inland as well as what's going on out to sea, the 100-year flood, for instance, could truly be a combination of, say, a 50-year riverine flood coinciding with, say, a 25-year coastal surge. We use our stochastic model to sample from this multivariate parameter space and simulate plausible flood co-occurrences for given frequencies in coastal catchments. As for the climate change component, we're optimists here. So we used representative concentration pathway 4.5 and produced not only the 2020 climate adjusted view of flood hazard, but also projected this out to the not so distant 2035 and 2050. At the coasts, we simply updated mean sea levels to those projected under this RCP, and also took synthetic hurricane events simulated using the different time horizons, atmospheric conditions. For pluvial floods, we took extreme rainfall simulated by both GCMs and the hurricane model and contrasted those with rainfall simulated under historical climate conditions. The derived change factors were then applied to our NOAA intensity duration frequency relationships. For the fluvial model, we used the HBV rainfall runoff model to simulate the streamflow response to each scenario's GCM and hurricane rainfall in each scenario's atmospheric conditions. Again, this was contrasted with respect to our historical HBV simulation, and change factors were then applied to the extreme RFFA flows. So that's the long and short of the methods. The output of these models has been released by the First Street Foundation on floodfactor.com. This makes it straightforward for members of the US public to understand their flood risk, both now and into the future, in an easy to use and consume interface, which gives each property a score out of 10, known as its flood factor, with 10 being extreme risk. This information is now also embedded in realtor.com to ensure prospective buyers are aware of the risk of flooding to properties they may be interested in purchasing. You may have been aware of this at the time, as a ton of mainstream media outlets covered this extensively back in June and July. So what? Asked the scientists in you. Fear not, this process has lent itself well to extensive model verification. Again, manual labor is key here. Where there are any discrepancies with local information, such as historic flood events, local models, and insurance claims data, these are flagged and reviewed by First Street and fed back to Fathom to recalibrate the model. With mass consumption of these data comes mass feedback. Here's just one example on Twitter where someone with incredibly local knowledge of flood behavior can verify whether the model is behavioral or not. The First Street team have formalized this process on floodfactor.com, where local flood experts and members of the public can flag discrepancies, and these can be reviewed and resimulated as necessary. The whole process is iterative by design, where, like a fine wine, the model gets better with age. So on to the validation metrics. Here we compute the output, we compare the output of our national scale flood model to those built locally from the ground up with in situ data by skilled engineers. While it seems hypocritical to criticize the FEMA approach and then benchmark against it, we should stress that recent models built using high-quality methods locally are the gold standard, and they produce flood extents we should aspire to resemble. The problem is that these models do not exist in enough areas to manage America's rising flood risk. To quantify skill, we use the Critical Success Index, which is a measure of how well our model fits the benchmark model. Given the uncertainty shared by models regardless of provenance, a fit score of around 70% is subjectively considered to be skillful. In these figures, we compare ours and FEMA's models. In blue is where they agree, in red is where we overpredict with respect to FEMA, and in yellow is where we underpredict. We exclude areas of pluvial flooding that are not modeled by FEMA, and also permanent surface water. In the comparison, we get a fit score of 0.78. In brackets is the old model's fit score. It's nice to see even the old model version being highly skillful, yet even this has been improved upon at large scale. Obviously, since the old model had no coastal surge component, performance improves drastically at the coasts. We repeat this comparison using the suite of very high quality flood maps generated in the state of Iowa by the Iowa Flood Center. The top panel is the old model comparison, the bottom is the new model. Again, we see improvements on an already highly performant model. Testing the 100-year flood might be quite forgiving, however, since they're so large that it's easy to find lots of areas where the two models agree. We also look at the very frequent 5-year flood event in Iowa. You can see that false alarms have been brought drastically down in the new model, thanks to the new channel schematization and flow estimation methods. Further evidence of increased performance at short return periods can be found by using claims data from the National Flood Insurance Program. We compute the 5-year claim rate, finding that there's a greater than 1 in 5 chance that 1.7% of NFIP policyholders make a claim in any given year. The analogous figure from our model is the proportion of US building stock inundated by our 5-year flood. Since we're dividing claims by policies and inundated buildings by total buildings, the two figures should be broadly comparable. In the new model, we find extremely close agreement, a figure of 1.70%. In the old model, around twice as many buildings were flooded at this frequency, around 3%. You can see from the images here an example of how much more confined and fidelious the new model version is at the 5-year return period. There's of course so much to talk about, and only so much I can fit into this talk. The paper, which was a gargantuan effort by a load of scientists, is hopefully soon to be published in Water Resources Research. For now, it's a preprint where you can find more information. As for what's to come, well, we're doing more model validation, this time against historical events. You can contribute to that discussion paper in NHES. We'll also be exploring what the implications are for US flood risk quantification. For now, it's in the Foundation's report, where we find 70% more buildings at risk of flooding than FEMA. But in some places, particularly inland and in the West, we find hundreds of percent more. And risk continues to grow. In the not so distant future, 11% more buildings will be at risk of the 100-year flood. But you can see in parts of the East Coast, this figure is in the hundreds of percent for some counties. So to wrap things up, we've built an accurate continental scale flood model representing fluvial, pluvial, and coastal perils, as well as climate change. But this work opens up a bottomless treasure trove of research questions, particularly related to representing climate change in flood models. It's a relatively young field, so there's much to explore on how we should be using climate model output in hydrology, how we characterize extremes with short simulations. And it's also worth considering that, although we're introducing a new bias to the model, the changes that we see are often well within typical hydraulic model uncertainties anyway. How can we therefore make inferences with these uncertain data? That's all for now. If you have any questions, then please do drop me an email. Thank you.